This video will be on parametric equations and how to use calculus with parametric equations. Now, when you see the word parametric in a math context, this usually means that the equations are time dependent. And so here's an example of, here's a non-parametric equation. These are equations that we're used to seeing, for example, y equals x squared. Now, a parametric equation would instead be a pair of equations, and they would be x of t and y of t. Okay, and so with a parametric equation, you have a new independent variable, t, and then x and y both depend on t. Now, you do have to be a little bit, not clever, but careful about how you define x and y. I think for the most part you can pretty much write any two functions here, but you would have to be you'd have to do some algebra in order to solve for x or y explicitly without the t, and that's a skill that we're not really going to delve into in this video. But here's an example of a parametric equation. You could have x equals t and then y of t equals t squared, and what this basically does is say, if we were to solve for this, basically because x equals t, then y of t, which is t squared, also equals x squared. So we get the same graph, we get the same parabola, but the time means that now we're talking about the motion of a particle along this parabola. And so at t equals 0, you'd be at the origin. At t equals 1, you'd be at the point 1, 1. At t equals 2, you'd be at the point 2, 4, etc. And so parametric equations are useful because we can use them to describe motion, and then therefore we can use calculus to further describe that motion. Let's say that we have this pair of parametric equations, or actually this is one parametric equation, but let's say that we want to, of course this is calculus, so we want to find dy dx. Well, x is no longer the independent variable, and so what we need to do in this case is to essentially, you could think of multiplying each of the top and bottom of this fraction by 1 over dt, like this, and then rewriting this so that the fraction becomes dy dt divided by dx dt. And this becomes a very useful thing because now all we have to do is take the derivative here, y, or dy dt, or y prime, would be, let's see, t, because you'd bring down the 2, 2 times half is 1, subtract, so dy dt is simply t, and then dx dt is going to be t squared. And so basically you just plug those in. And so dy dt is t, dx dt is t squared, and so your answer for dy dx would be 1 over t. Notice that your answer will be in terms of t, that's okay. You just have to figure things out from there if the problem asked you to do more specific things. Let's talk about what the values of a derivative might mean. So for example, if you're looking for a horizontal tangent line, you're looking for where dy dx equals 0. Same thing here where we have the slope is horizontal, so you could say this is a horizontal tangent line. If you had dy dx equals infinity, or rather it might be easier to say that dx dy is 0. So if dx dy is 0, then we end up with a vertical tangent line because this is an undefined slope. And so the best way to go about finding a vertical tangent line, because the bottom needs to equal 0, and this dx came from dx dt, we essentially want to set dx dt equal to 0 for a vertical tangent line. And similarly, we want to set the top equal to 0 for our horizontal tangent line. So you would set dy dt equal to 0 for a horizontal tangent line. You do need to make sure that dx dt and dy dt are not 0 at the same time. That could happen, and essentially what happens there is that the particle stops for a second and then keeps traveling. And so there you might have a situation where the particle is moving, stops in both directions, and then could start in a completely different direction again. You would end up with a cusp, which is not differentiable. So you'd have to check that for vertical or horizontal tangent line. We do have to alter our arc length formula for parametrics, because instead of having f prime, which was dy dx, and squaring it, we need to go back and think about it. So the formula that we'll work with is the square root, or a to b, and then square root, and we'll sort of go back to the idea of that initial triangle where we had dx and dy, but now because it's time, we have dy dt and dx dt, and so we can use the Pythagorean theorem to write out, we'll have dx dt squared plus dy dt squared. However, in this case, notice that the original length that we wanted is now divided by this dt term, because the dx and the dy were also both divided by the dt term. So when we calculate our length, what we have to end up doing is multiply back the dt. And so this is where the dt comes in for our integral with parametric arc length versus algebraically manipulating the inside to pull out the dt. So this is our arc length formula for parametrics. This is another sort of tricky variation of a problem. So instead of finding just the straight derivative dy dx, we're going to find the second derivative. And so the way we need to think about the second derivative is it's the derivative of dy dx divided by this dx. And so to see this a little bit algebraically, because it's dx squared, we're taking one of the dx's and putting it up here to make a dy dx, and then the other dx sort of stays down here. But now, in order to actually find this derivative, we need to let's first find dy dx. And so to find dy dx, we need to do the whole dy dt thing divided by dx dt. So dy dt will give us 3t squared, and dx dt gives us 2t. Simplifying this, we'll get, let's see, one of the t's will cancel, so we'll just get 3t over 2. Bringing down the original problem, now we have the derivative of 3t, we'll keep this in blue so we see where it came from. Now we have the derivative of 3t over 2, and we're taking that derivative with respect to dx, but now we can't do this because we don't have t as a function of x or something like that. And so we have to do the same dt trick here as well. We need to divide the top by dt and the bottom by dt. And so what ends up happening is we take the derivative of that first derivative with respect to t, that gets us 3 halves, and then we divide by dx dt again, and that dx dt is going to be 2t. And when we simplify this, what we'll get is 3 over 4t, which is the second derivative. Physically speaking, the second derivative represents acceleration, and so this would be the something to do with the acceleration of the particle as a function of time as it moves along the curve.